We're continuing with section 3.10, related rates, example 4. And in this example, a rocket is being launched to the space, and we're recording it from 4 kilometers from the launch pad. And there are two scenarios with this question. One basically is asking if the angle of inclination is 30 degrees and it's rising at 9 degrees per minute. How fast is the rocket at that instant going, and how high is the rocket? The other question is asking when the rocket is 10 kilometer high and rising at 8 kilometers per second, how fast is the camera angle increasing? So the two scenarios, both of them are involved with basically the height, and we're assuming the rocket is going straight up, perpendicular to the ground, and that's what we're assuming. And even though the rocket is kind of tilted out, but we're assuming it's a good approximation to go straight up, basically. And then so it involves that height, and it involves that theta. And in one way, if you look at part A, it's telling you about the value of both of these values are changing. Both of these variables are changing, or quantities are changing. In problem 1, we know the value at the instant for quantity theta, and we know the value for d theta dt. And then we're asked to find, it says how high is the rocket and how fast it's rising. So it's asking for h and dh dt. That's problem part A. Problem part B is the other way around. It's telling you that the h is at the instant value, and it tells you which is 10 kilometer at that instant. It's changing, but, and then it tells you dh dt at that instance is 8 kilometers per second. And then it's asking how fast the angle is increasing. And we know that these things are related to each other, and we want to know how they're related. If you look at all the values in here, you see that basically h is changing, theta is changing, this distance in here is also changing, but the only thing that is not changing is the distance of the cameraman and the launch pad. So now let's try to connect the variables together. Again, here is the h over here, and here's theta, and there's a 4 kilometer down here. And so I can connect these in this manner. Tangent of theta is equal to h divided by 4. Now let's take the implicit differentiation of both sides, remembering that theta and h are both changing with respect to time. That makes both theta a function of t. I don't know what function of t it is, but it's a function of t, and h is a function of t. This could be, let's say, t squared plus 1. This could be 2t plus 5, or so on and so forth. I don't know which one it is, but remember that they are functions of t. I just don't know the rule of the function. And usually there's good approximation with these things, but we're assuming we don't know any of those approximations. So now, first I figured out my quantities. I figured out which one's constant, which one is not. And then the next thing is I set up my nice geometric picture. Now I related the quantities that I have to the quantities that I want, And now it's time to take the implicit differentiation. And so in here, what's the outside function is tangent of u. And so the derivative of tangent of u is secant squared u. And that's the derivative of outside with respect to u. And then derivative of inside, which is that. And in here, it's 1/4. I can take the 1/4 out of this. This is 1/4 of h, right? So I take the 1/4 out, and it's derivative of h with respect to t. Now, what do I have? What do I need? One thing that I know is that I know theta, and theta is 30 degrees. And I can, for matter of plugging it into the trig function, I can plug it into the trig function. But something to notice, and it's very important, is when you're not plugging it into the trig function, and it's just finding the, let's say, the rate of change in theta, it has to be in terms of radian. And so you cannot have degrees per minute. You have to convert to radian per minute. So let's calculate all these. First of all, 30 degrees is going to be equal to pi over 6, right? So that one is settled. And then what is secant? Secant is 1 over cosine. So cosine of pi over 6 is going to be equal to square root of 3 over 2. That one's good. And then what else do I need? I need to convert 9 degrees into a value. And so 180 degree is pi. Then 9 degree, and that would be, you're decreasing it by what factor? By factor 20. So it's going to be pi divided by 20. So I have 9 degree per minute is pi over 20 radian per minute. And so I'm writing it in here. Secant squared is 1 over cosine of pi sixth, which is 2 power 2, which is square root of 3 over 2 to power 2, and times pi over 20 is equal to 1 over 4, and rate of change of h. So now I'm finding the rate of change of h, and that is going to be equal to multiplied by 40, that's pi over 5. This one is 3/4, and so on the other side I have 4/3, and then I multiply it by 4, multiply it by pi over 20. And then we figure out the value, and one piece is left. I'm going to erase this and come back, but we want to figure out what h is, and we want to figure out the value of the rate of change. So before I finish this up, this is going to be 4 pi over 15 kilometer per second, which this is approximately 0.8 which is approximately 0.8 4 kilometer per second. So it turned out that I didn't need the height of the rocket to figure out the to figure out the rate of change of the rocket in this case. But let's calculate it anyway. And sometimes we have to calculate one of the quantities to be able to calculate all the rates of change. And so in here, if I'm calculating the height of the rocket when the angle is 30 degrees or pi sixth, the relationship, again, we said that tangent theta is equal to h divided by 4. That is tangent of pi over 6 is equal to h divided by 4. And so tangent of pi over 6, sine of pi over 6 is 1/2. Cosine of pi over 6 is square root of 3 over 2. Therefore, it's 1 over square root of 3 equal to h over 4. So h is equal to 4 over square root of 3 kilometer. And so you calculate that. And the answer is approximately 2.3 kilometer. That's the height at the moment. Now we're doing part B, and again, now let's do part B of the same example. And so this time around, the h is given. H is equal to 10 kilometer, and dh dt is given 8 kilometers per second. Draw the same right triangle, theta here, h here, 4 is constant, and then now it's asking to find the rate of change in theta. It doesn't tell you theta, and it's not asking for theta, but we may have to find some quantity related to theta also. So now I'm going to set up the same relationship as I did in part A. Again, I'm relating h4 and theta, and that's how a tangent of theta equal to h over 4 is the relation. Then I take the implicit differentiation, I do the implicit differentiation, and I get secant squared theta d theta over dt, and 1/4 of dh over dt. And then the next part is, well, I know what dh over dt is. I just said that's 8 kilometers per second. But I don't know if and I know that I'm supposed to find this quantity. And to find that quantity, I have to know this quantity. Can I figure this quantity, the first one, secant squared theta, by the information that I have to plug into this, into the derivative and find the quantity that the question is asking for? So that question can be answered using this Pythagorean, using this right triangle and a Pythagorean theorem. So we're saying that at that instant, h is going to be equal to 10, right? And so using that fact, I can actually say that. And what am I trying to find? I'm trying to find secant of theta. Secant of theta is equal to 1 over cosine theta. So I'm really looking for cosine theta. Cosine theta is adjacent over hypotenuse, and hypotenuse is basically this side. And I can go with 10 to power 2 plus 4 to power 2 and square root of that. 10 to power 2, 4 to power 2, and gives me 116 over here. And so that's the hypotenuse. So cosine theta is going to be 4 over square root of 116. And then secant squared theta is going to be the opposite, the reciprocal of that. So I get 1 over 16 over 16 d theta dt equal to 1/4 times 8. And then I calculate. So computing d theta dt gives me, multiply this is going to be 2, that these two simplify, I think, to 4 and 29, and so you get basically 8 divided by 29, which is 0.28 radian per second. From there, again, all these computations with derivative is always involves radian.